In the wood-panelled chapel of the Catholic University of Leuven in Belgium, a priest lights a candle and kneels before the statue of Christ for his daily devotion. His name is Georges Lemaitre, and it is 1927. As he rises, his eyes wander to the towering windows that line the chapel's walls, and to the stars twinkling in the early evening light. He smiles in distant reflection, imagining the sequence of events that brought that starlight to the Belgian sky. But, despite his faith, Lemaitre's beliefs were lacking a creator so fundamental to the Catholic doctrine. He had no need for divine intervention when it came to the making of the universe. No seven-day miracle. Instead, he saw it as a natural consequence of natural laws and processes proved by mathematics and visible in the movements of the heavens themselves. His extraordinary insight would earn him 2 Nobel Prize nominations. For Georges Lemaitre was more than just a Catholic priest. He was also a theoretical physicist, a cosmologist fascinated with the workings of God's perfect universe. It was here in Leuven that he began work on a theory that would come to shape our modern understanding of the cosmos, all based on the remarkable observation that space seemed to be expanding. Mathematics had laid out the history of the universe, and now Lemaitre traces it backwards in his mind's eye. He imagines a time before humans or indeed any living thing inhabiting the Earth. Before that, of course, the Earth must have formed as a barren rocky ball around the glowing sun. Before that, the sun ignited in a blaze of nuclear glory, crushed into being by the irresistible force of gravity in a vast cloud of gas and dust. That gas and dust was a consequence of many generations of stars living and dying before our own, igniting, fusing elements and exploding in terrific supernova that spread their elemental waste products across the cosmos. He imagined a time before these many lineages of stars, before the chemical complexity that we enjoy, when only hydrogen and helium floated inert in a lightless universe. If space is expanding now, then in the reverse chronology of Lemaitre's mind, it is contracting. There would be a point in this dark, gassy cosmos before the first star, when all the matter in the universe was compressed into a vastly smaller space. Atoms would become packed so tightly that even photons are unable to pass through. There are no light sources here, but it doesn't matter. The universe is utterly opaque. When the contracting reversed universe crushes down even further, the atoms themselves are crushed, first into subatomic particles and then into pure energy. In this small, dense universe, there is only radiation. Here, even Lemaitre's imagination begins to falter. The universe can become even smaller, even hotter. But what happens then? Lemaitre pushes the unanswerable from his mind, content in having grasped 13 billion or so years of cosmological history, and unperturbed by the mysteries contained within the first fraction of a second. But the Big Bang Theory, of which Lemaitre was unknowingly the first true proponent, has been the subject of debate, research, and speculation for nearly 100 years. How did the universe begin? What was the trigger for its incredible expansion? And could our simple matter brains ever even comprehend the real truth? Before Lemaitre, studies of the cosmos had largely focused on our own place within it, as well as observations to determine its composition and extent. The 13th century philosopher Sigurd of Brabant was alone in venturing the statement that the universe was eternal, with no beginning. His heretical views outraged the theologians of the time and earned him condemnation by the Pope in 1277. Rumour has it he was murdered with a pen, a symbol of the damage his ideas had done. Since then, no serious scholar had contemplated changing history, or a beginning. And so Lemaitre's calculations rocked the cosmological world. But they were not embraced by everybody. The idea was that the universe started its life a finite time ago in a single huge explosion, and that the present expansion is a relic of the violence of this explosion. This Big Bang idea seemed to me to be unsatisfactory even before detailed examination showed that it leads to serious difficulties. One respected but controversial astronomer, Fred Hoyle, railed against Lemaitre's expanding universe history, even coining the term Big Bang as an insult. For the implication of an expanding universe is that, at some point, it must have begun expanding, and at some point the universe itself must have begun. This, Hoyle confidently declared, was pseudoscience, little different from trying to justify the existence of a creator. The only reason, he said, that we were so attracted to this novel Big Bang theory was because the teachings of the Book of Genesis are so ingrained into our collective psyche. And yet, Lemaitre was quite happy to keep physics and religion separate. His mathematics didn't yearn for theological validation, and they were supported by real observations of the real universe, made by eminent astronomer Edwin Hubble just a few years later. From the Mount Wilson Observatory northeast of Los Angeles, Hubble had gazed tirelessly through the largest aperture telescope of the time, peering at some of the dimmest parts of the night sky. His measurements would prove conclusively the long-held suspicion that there were more galaxies than just our own Milky Way, but they would also show something that nobody had expected. Luminous objects, like stars, emit light as a result of the fusion in their cores. The colour and characteristics of that light depends on the temperature and the composition of the star, but it also depends on the star's movement. Just as an emergency vehicle sounding a siren will sound different when it's moving towards us or away from us, so too the light from the star will be altered when it's moving closer or further away. In sound, the phenomenon is known as a Doppler shift, and in light, it's redshift. The light waves emitted by stars moving away from us are stretched out. The same energy must now cover a greater distance, so the wavelength is subtly increased. In the visible spectrum, the longer wavelengths of light are coloured red to our eyes, and so receding stars appear more red than they actually are. Hubble wasn't the first to discover redshift in astronomical objects, but his observations at Mount Wilson did uncover a surprising truth. Every galaxy he studied was redshifted. Every single galaxy was moving away. Although at first this would seem to support religious notions of the Earth being the centre of the universe, the truth is stranger still. Hubble saw that the more distant galaxies receded much more quickly than those close by, and this could only be possible if the whole of space was expanding. These observations were a striking vindication of Lemaitre's mathematics and of the concept of a tiny beginning to our universe. In 1964, researchers at Bell Labs in Holmdel, New Jersey, were using a gigantic horn antenna to tune into radio waves bounced off some of the earlier satellites. The work demanded unprecedented precision, and the scientists went to great lengths to eliminate all possible outside sources of interference. But, despite their best efforts, their results were plagued with a persistent noise they couldn't eliminate. At first they thought it could have been the results of pigeons roosting in the shelter of the huge antenna, their droppings disturbing the signal. Or perhaps it could have been interference from bustling 1960s New York City, some 50 kilometers away. But eventually it became clear that the noise wasn't pigeons or people. It was coming from outside our galaxy. It was a property of the universe which we now recognize as cosmic microwave background radiation. This radiation is a remnant of a time when the universe was very small and very, very hot, as predicted by Lemaitre's calculations. The expansion of space has since spread that radiation out, stretching the once intense heat waves into microwaves, with a background temperature of just 3 degrees above absolute zero. These radiation scars burned into the fabric of space are vindication of the truth of the Big Bang. The Big Bang Theory is now the accepted model for the cosmos, a picture of expansion over some 13.8 billion years. But there is still much work to be done, much understanding to be sought. The nature of the universe's first moments are still shrouded in mystery, and so many questions remain unanswered. What really was the Big Bang, and why does it break our understanding of the universe? Georges Lemaitre's models of an expanding universe were originally based upon Albert Einstein's theories of general relativity, which he had formulated some 20 years earlier. But when Einstein heard about this radical new theory, he was uncomfortable. He declared that Lemaitre's maths were sound, but his physics was atrocious. The problem was, once again, the implication that an expanding universe must have had a beginning. But here it wasn't the theological arguments that cast it into doubt, rather the fact that the physics of the time had no explanation for how such a thing could happen, or what it even looked like. Lemaitre extrapolated the universe back to what he describes as the primeval atom, which contained within it the potential for the entire immeasurable universe. We can trace the beginning of time and space back to this single point, but as for what it looked like, or how it worked, even now, physicists aren't sure. When all the stuff of the universe is compressed into an increasingly smaller space, the laws of physics dictate that the density will increase, and so will the temperature. We have a good idea of what happens to matter under these kinds of conditions, thanks to small-scale experiments in gigantic particle accelerators. But our experiments and our understanding can only go so far. After that, things become unclear. Beyond the realm of particles and subatomic quarks and their mysterious companions is a compressed universe of pure energy, where weirdness rules. The fundamental laws of physics which govern everything we see and experience break down. It becomes harder and harder to predict how this hyperdense and hyperhot primeval universe worked. How small could it really get? What makes it begin to expand? In the last few decades, theoretical physicists have grappled with tentative theories. One that reigned for a long time is that the cosmos began as a gravitational singularity, a single one-dimensional point from which all of time and space were birthed. This is not dissimilar to the singularity at the center of black holes, like the one that lurks at the center of our galaxy. The singularity is a point that is so immeasurably dense that the gravitational pull from it reaches infinity. In the case of black holes, the gravity is so strong that light cannot escape. But a singularity at the beginning of the universe would have no light to consume, as it already contained everything there was to contain. If the universe today is infinite in extent, then the infinitely small singularity would have a density and temperature that would also extend to infinity. Concepts of infinity stretch our minds to breaking point. And that's not the only problem with gravitational singularity as a starting point. If, at the moment of its beginning, the cosmos had been an arbitrarily dense and hot point, then scientists believe the universe that resulted from it would have looked very different from the one in which we find ourselves. There should be huge fluctuations in temperature and density from one end of the cosmos to another. And there aren't. There should be ultra-high temperature relics of the infinitely high temperature state. But there aren't. Space itself should be more lumpy. But it isn't. In fact, the universe is remarkably uniform when looked at as a whole. The fluctuations in temperature and density that we see average out, and you would struggle to pinpoint yourself in space based on these kinds of features alone. Cosmologists go so far as to say that it is smooth. and the chances of a singularity creating a smooth universe are infinitely small. But there is another option. It may have all begun with a period known as inflation. During this inflationary period, right at the earliest moments of the cosmos, space expanded exponentially, doubling in size from one moment to the next. Things that increase exponentially get very big, very fast, and so this cosmic inflation was sufficient to put the bang into the Big Bang itself, expanding much faster than even the speed of light. It was enough to stretch the universe flat and to make it uniform all over, which is precisely what we see today. According to the theory, the universe was imbued with energy, which caused the exponential expansion. When the exponential expansion ended, although we don't know why it ended, the energy inherent to the universe is converted into matter and radiation, marking the beginning of time and space as we understand it. The features of the modern universe only allow us to see the final decillionth of a second's worth of this inflation. That's 1 over 10 to the power 33, during which time physics made a little more sense, but we still don't know how long the inflationary period lasted. Could the inflation itself have started with a singularity? Logic says no. If exponential expansion means doubling in size, then running that in reverse, we see the universe shrink to half its size, then a quarter, an eighth, a 16th, and so on. The fractions become vanishingly small, but they never reach zero. From a purely mathematical point of view, a singularity of zero size is an impossibility. So, right now, we don't have the tools to understand or describe inflation any further back. We may never understand it. The origins of cosmic inflation extend back into the fog of pre-time, beyond the reach of science and into the realm of pure speculation. Thus, the Big Bang is perhaps not the beginning of the universe at all, but rather the line drawn in the cosmic sand, marking the limits of our own understanding. Not a beginning, but a history whose opening paragraph may be several pages in, but is the first to make any real sense. And yet, if we really stretch our minds to the limit of our comprehension, the extreme edges of theoretical physics may give us the tools to break through that fog. In 1981, in the shadow of St. Peter's Basilica in Vatican City, the top cosmologists of the time met for a conference organised by the Pontifical Academy of Sciences. Gone are the days when the Pope would issue condemnations of cosmological thinking, or perhaps it is precisely because the favoured Big Bang theories now point towards a mysterious beginning for the universe that theological institutions see parallels of their work in mathematical cosmology. Regardless, at this conference among the hushed gardens of the Vatican, 39-year-old Stephen Hawking is an honoured guest, and he presents some of his latest thinking on the beginning of the universe. He addresses the assembled scholars, his own voice cutting through the last shreds of muttered conversation. His disability has already begun to take its toll, and a close friend sits alongside him, translating his words for others in the room to understand. But while his words may seem ill-formed, his thoughts have never been clearer, even if they too seem to make no sense. The universe is finite, he says, but it has no edge. Someone standing at the far end of the observable cosmos, 13.8 billion light-years away, would see space exactly as we do. As you go back to the beginning of the universe, space and time become fuzzy, but they curve around and cap off, much like the South Pole of our planet. Trying to understand what came before the universe is like asking what is south of the South Pole. The question itself is meaningless. Hawking's no-boundary proposal rocked the scientific community and left the rest of the world scratching their heads. While we may understand that there is nothing south of the South Pole, seeing that in the context of all of space and time is a difficult concept for us to grasp. As we strive to understand our place in the unfathomable cosmos, we can't help but grasp for answers to potentially unanswerable questions. What was there before? What is the universe expanding into? And why did it start at all? Testable science cannot give us the answers we seek. Time is a fundamental property of the universe in existence, and so there was no time before the Big Bang. There was no before. Space is a fundamental property of the universe in existence, so there was no space before the Big Bang. There is no outside. The cosmos just is. Something that breaks all the laws of physics is impossible to visualize, let alone study. But even in the face of the truly mysterious, the modern scientific approach isn't content with simply saying that we don't know, that we can't know. Scientists continue to speculate. They take an obscure property of the universe or a mathematical concept and run with it to come up with speculative theoretical possibilities that might, just might, give us a pinhole view into the impossible before and the intangible why. One of the most popular pieces of speculation has become known as the Big Bounce, in which the universe is eternal but transitions between an expanding state, described by the Big Bang, and a contracting one, known as the Big Crunch. The idea of this endlessly inflating and deflating cosmos has been around since the early 20th century, but it was only in the last decade or so that physicists have discovered how it might be possible. The theory posits that in the very earliest moments of the universe, everything is so small that reality is governed by quantum mechanics. The strange properties of the quantum world mean that a contracting universe can be saved from complete collapse by quantum tunneling from a point just before the collapse to a point just after it, transitioning instantaneously from a contracting space-time to an expanding one. At the other end of the universe's timeline, after a Big Bang-style expansion for billions of years, it's hypothesized that the density of matter in the cosmos will have sufficient gravity to overcome the force driving expansion and eventually reverse it. But the latest observations of the modern universe suggest that the expansion Hubble saw back in the 40s is not, in fact, slowing down, but is actually accelerating. This is a spanner in the works for the Big Crunch, but there is another option. In 2010, British theoretical physicist Roger Penrose presented a new theory of conformal cyclic cosmology, founded in some of the most complex mathematics and theoretical physics available to cosmologists today. The model relies on the concept of conformal geometry, which concerns the geometry of shapes, irrespective of their size. A chessboard has the same geometry, the same number of squares, the same aspect ratio, regardless of how big it is. Whether it's a tiny, pocket-sized board or a huge garden set, the game is still played the same. And these principles apply to our own universe, at the points in its history when we lose track of scale. One of these points is in the murky, high-energy instant just before the Big Bang. The other is in the far distant future when black holes have swallowed everything and the overall energy is so low that all space and time cease to have any meaning. Although many would consider a tiny hot universe and a huge cold one to be about as different as it's possible to be, according to conformal geometry, they are equivalent. A huge cold universe at the end of its life behaves just the same as a hot one at its beginning. Penrose uses these mind-bending principles to reason that one naturally leads on from the other, that we are living through a single eon of our universe, and that in a googol years or so, the loss of scale at the death of the universe will lead to the Big Bang of a brand new eon, and the beginning of a new history. In both the Big Bounce and conformal cyclic cosmologies, our Big Bang is both a beginning and an end, and is just one of many Big Bangs in the endless stream of universal existence. But there is an even stranger theory, with its origins in strings. In the spring of 1995 at the University of Southern California in Los Angeles, the American theoretical physicist Edward Witten made an extraordinary announcement that was music to the ears of string theory scholars worldwide. String theory models had been developed over the preceding 50 years to explain the fundamental nature of matter on an unimaginably small scale. It claims that all particles are ultimately composed of one-dimensional strings that move through space and interact with one another. But to explain everything in our universe, different versions of string theory argued that there must be other entities with more dimensions, two-dimensional sheets or three-dimensional volumes, and even more. This model, which was intended to unify all of physics, had done little more than divide the scientific community. But Edward Witten rejected such divisive thinking. He conjectured that all the different versions of string theory could all be true, if they were incorporated into an 11-dimensional reality. His proposal of this so-called superstring theory sparked a flurry of research and offered a new, if perplexing, possibility. In superstring theory, space-time is described by no less than 11 dimensions. In this theoretical framework, our own universe, which we experience in the 3 dimensions of space and 1 dimension of time, can be considered a mere portion of the whole, a so-called brain in the bulk of hyperspace. Physicists suggest that our universe developed from the energy released when higher-order brains collided. The energy from the collision provides the motion force for the Big Bang and subsequent expansion of the universe, but it can't last forever. Tension between these higher-order brains will cause them to retract and recollapse after a mere trillion years, bringing an end to our universe that we are unable to visualize or even comprehend. This heady theory is known as the ekpyrotic model, referring to ancient myths that see the world born in a fiery explosion. For now, we have no tools to detect the higher dimensions if they really exist, so like the other theories that try to explain and justify the cosmos, they remain little more than highly informed speculation. But the Big Bounce, the conformal cycles, and the ekpyrotic brain cosmos are all possibilities that lie at the bleeding edge of modern cosmology. Like all good theories, they try to make predictions that we can test through observation and experiment. But so far, no evidence has come to light to give us any real clue. Our understanding of the cosmos relies, like a house of cards, on our understanding of physics and mathematics, which continues to change and evolve. The true nature of the Big Bang and the meaning of the universe as a whole may always be incomprehensible to our monkey brains. Or perhaps a new revelation will turn everything on its head tomorrow. We can only keep asking and trying to see through the fog. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. And we'll see you next time.